Yeah, all of them. Okay. So combustion, I would argue, is sort of one of the harder ones. Right, so one approach with this one that I've been hearing a lot of people doing is zooming in on the entropy aspect, okay, which is a good first start. We've been talking about entropy, so it makes sense to practice with that. So we could look at our entropy change for combustion. What would we expect? Should the entropy go up or down? Up. Why?
You start just looking at it, even though you've got two reactants and two products, you still end up with...
I'm going to pull you back just a little bit on that. You should look for something else before that. The state of matter. The phases. So before looking at those amounts, first look for those phase changes. There was no phase change, so you advanced, and then you went through and said there's 2 on each. Arguably, I, again, wouldn't say 2 on each. What I'd be saying is there's 6 on the left, and there's 7 on the right. Okay? Which suggests that our entropy goes up because we're looking at more molecules potentially moving around. Okay? So that would suggest we have a positive delta H. So for A, we should be somewhere in this column. Now we have to evaluate the delta S. Now we have to evaluate the delta H. Right? It doesn't state whether it's exo or endothermic. Why does it not state it? This can sometimes be a dangerous assumption to make.
It says combustion.
It's combustion. So what are we relying on? Prior knowledge. You have to have prior knowledge that a combustion reaction is exothermic. And if it's exothermic, what does that mean? You have a negative delta H. Our 2 quadrants, or our 2 lines, effectively meet in one quadrant, and that would be in that upper right-hand corner. And we would call that one A, always spontaneous. Okay? That prior knowledge can be a dangerous one. Unfortunately, sometimes it's going to show up, so you got to watch out for those. Okay? With combustion, you're burning organic matter. You're reacting oxygen with an organic piece of material. We put wood and we put it in a fireplace. Why? When we start it on fire, we do a combustion reaction to produce heat, so it warms up our house. That was the point of burning the log. That was that combustion process, is that heat was a product in that case. I like to explicitly state where my heat term is showing up so that I know where it's navigating the system. If we look at photosynthesis, for the next one, what's it go through and give us right away? It's endothermic, which means a couple different things.
Positive delta H.
Heat's on the reactant side. That would also correspond to a positive delta H. So we're in this line. What happens with the entropy? Where do we start? Phases. I have a liquid which is effectively non-existent versus the gas versus gas and solid over here. Okay? So what we're evaluating is those particles. So we could then go through and look at our number of gas particles on both sides. Right? Because we have liquid and solid. We look at the gas particles. Is there a difference? No. And this one now starts to hit kind of a gray area on how we would navigate this. Right? If the gases aren't really panning out as a difference, maybe we should shift to looking at the other phase. We can look at the liquid turning into a solid, which means a decrease in entropy. And if we have a decrease in entropy, that puts us in the negative delta S, which then says it's non-spontaneous. Does that match with what you would understand? Right. Does it make sense that if I just mixed carbon dioxide and water that it turns into sugar? That's never going to happen. We have to supply something to force that to happen. That's the whole point behind plants, is they're supplying that extra process to be able to navigate that system. Where's my eraser? There it is. Okay. Salt dissolving in water. What happens with your entropy? Okay. We're looking at two aqueous things as opposed to a solid. That should be an increase, which gives us a positive delta S. Now what? When you mix salt with water, have you noticed a temperature change? Most people probably haven't. Okay? So let's look at it more chemically speaking. What's happening as we transition from the solid to the aqueous? What did we have to do? We had to break a bond. What does that mean? All the way back to the beginning of the unit. That requires energy. Which means heat is on the reactant side, which means endothermic reaction. Okay? It's a little bit weird referring to it based off of your enthalpies there, but it's requiring heat. Heat is needed to go in, which means we're looking at a positive delta H, which puts us in this lower left-hand quadrant. For that one, what color will we see? Spontaneous at high temperatures. Kind of makes sense? How about boiling water? What do we see? An increase in entropy because liquid to a gas. An increase in entropy means, again, we're looking at our positive delta S. Where's the heat? It's on the reactant side. To boil water, it requires that I add heat to force the phase change. That would be our heat of fusion. I haven't taught that in a long time. Okay, I think that's our heat of fusion. It's one of our heat of phase changes. Right? So if heat's on the reactant side, that means positive delta H, which means, again, spontaneous at high temperatures. Does that check out? Yeah, if I'm at really high temperatures, would I expect liquid to transition to gas? Yeah. What about freezing? Freezing is always a weird one in my opinion. So it's a decrease in entropy. What does the decrease in entropy mean? We're looking at that negative side. Okay. Where's our heat term? We're removing heat, which means the heat is where? It's on the product side. Have you ever walked around near a refrigerator? What do you feel? It's hot. Why is it hot around the refrigerator? To keep the inside cool, what does it have to do? Push all the heat to the outside. It's an exothermic process. All right? If we're looking at heat on the product side, we're looking at a negative delta H. Did I pick a color for that? I'm not sure I picked a color for that. Okay. A negative delta H with a negative delta S, right? Spontaneous now at low temperatures. I shouldn't have boxed that. I should have said E. Making sense? All right. How about mixing oil and water? All right. So, and I forgot to mention that. Okay, jumping right to the answer, not spontaneous. Okay, that works when you have an experience of what is being presented. What if you don't have experience with what is being presented? You would need to break down the theory that gets you to that answer. What's the theory that gets you to the answer? Okay, so we're hearing a statement that F should be here, not spontaneous. What's your theory that gets you there? That the entropy is negative and your enthalpy is positive. That's your theory. Is it true? we have oil and water. They're two phases, right? If I mix them, what happens? Increase or decrease in entropy? Here's my water particles, where I start. Here's my oil particles. If I mix, what does it look like? Is that a decrease or an increase in entropy? That's an increase. That's a positive delta S. Why is that problematic? We said it was negative because we jumped to an answer as opposed to slowly piecing our way through each of those individual steps. Break it down slowly. This is a positive delta S. We've increased the possible places where our individual particles can exist. We have more microstates in the mixed state than we do in the unmixed. That's a positive delta S, not a negative delta S. Okay? What about the enthalpy? What has to happen to transition to the mixed state? I have to add heat. What's that heat doing? Why? What's the heat doing?
It makes it more like soluble.
Why?
Oil and water don't mix like at room temperature.
I don't care. What's breaking when I mix them? Do I still have water molecules and oil particles? Yeah, so I'm not breaking anything, am I? This might help if we drew out a water molecule. If I draw a second water molecule, does it matter where I draw it? Yeah?
You're breaking the hydrogen bond.
Ah. When we look at pure water, there's a hydrogen bonding interaction. When I go to the mixed state, what happened to that hydrogen bonding interaction? It's broken. I have to break that intermolecular force to force the reaction to happen. How do I break it? I add heat. Heat is now a reactant, which means my delta H is positive, which now puts me F in that system. Neat. Following each of those individual processes. Okay. Slow it down. Think about what's happening at each of those individual steps between your enthalpy and your entropy and slowly build that into this table so that you can then predict what's happening with your spontaneity. We good? Cool. We've got just kind of a summary slide here talking about our phase changes. As we go from solid to gas, our entropy increases. All right, so we could look at freezing and boiling and talk about the different changes in both our heat terms and our delta S terms. Those were things that we literally just walked through and talked through, but here it's now being presented in a single slide. It looks like lots of people want to write this down, so I'll pause and let you write this down. All right. That said, why do you need to write it down? Do you have the slides? Okay, just, throwing that out there. But I'll let you write it down. Okay, that was enough thought games. Let's go ahead and do an actual calculation. Hooray, calculations. Okay, so calculate the I'm doing it now. The entropy change for the chemical reaction. All right, this means we would need a formula. What's our formula? Okay, I'll leave it at that and let you go through and work that out. Okay, as you're working it out, I'm also going to work it out. It's always fun to have a little competition in race. Why not? Okay, I'll give you a head start, and I'll talk over you so you can't think. Okay, so if we go through, we take our products. Okay, we have to add our products. We didn't note that in our formula, right? It was the sum of our products. That's a goofy looking sum letter. Let's try that again. Okay, minus the sum of our reactants, right? Okay, can I run the calculation as written? No, why not? What's that?
Go to add first, right? Oh, you're supposed to. Actually,
In this case, we're not going to have to stress about that minus sign distribution. We've talked about that already, right?
Yeah.
Okay, so we don't have to stress because there was only one reactant, so there's no minus sign that I have to distribute a long way. So I could just run a calculation right now, but my question again stands, am I allowed to run this calculation? No. Why am I not allowed to run the calculation? Mathematically, it's fine, but I'm not allowed to do it as is. What's the issue? I meant to provide a bigger hint by having it color-coded all the way through, and I screwed that up, but someone already caught it. The units. This is 38.1 joules per mole of what? Calcium oxide. This is 213 joules per mole of CO2. Those are different units. Can you do that calculation? No. So how could we possibly do this sum if the units don't align? What's missing from our formula? Remember there was a little n in front of it? That n represented the moles from our balanced from our balanced equation. Okay? I don't know what you would potentially see in the future, but this equation is balanced. Balanced? Yeah, okay, I should check. It is balanced, so those end up being ones, which means this first one is 1 mole of calcium oxide. What happens? The mole unit cancels. Once the mole unit cancels, now everything's kosher and I can go through and run that calculation. Does that make sense? Okay? So don't forget your units through these processes. Okay? I could easily see Alex giving you an equation that was not balanced, and you have to balance it before you run the calculation. I don't get the feeling that's something Dr. Schneblin would do, but I could be wrong. Does that make sense? So officially, we'd also have to build out our 1 mole, what was this one? I already forgot, CO2. And our 1 mole of our calcium carbonate. So far, so good? Okay. Now we could run the calculation, and I believe the answer we get, ballpark, is 160 joules per Kelvin. There's now no more moles. Okay, make sense? Is it actually 160.2? Yeah, look at that. Sometimes numbers stick. Okay. I would also add an extra little piece of information. For me personally, because I know I would get confused. Okay. We already had a small conversation. I said, did we already talk about the importance of that minus sign? Yeah. Okay. We talked about it because I know as an individual going through and running these calculations, I lose track of that minus sign a lot. So if I'm going to go through and calculate my entropy, I'm not going to leave it at 160.2 joules per Kelvin. What am I going to write? Positive 160.2 joules per Kelvin. That positive is to add that extra emphasis so that I'm looking at a change. I can now define that, and I can be happier with that result. Okay? The other thing that's nice about this is I can check my work. This says the entropy goes up. By inspection, would I expect the entropy to go up? Chemical equation, I start with a solid and I end with a gas. Yeah, the entropy should increase. So getting that positive value is a nice double check to ensure that the calculation that I'm running, I didn't goof my minus sign somewhere through that system. Make sense? Cool. We good? Oh, and I'm going to make another apology to Dr. Chavons. I have no idea why this slide is here. I just don't. So we talk about cement a whole lot. If we're actually talking about its setting, it's an exothermic reaction. Yay. Sorry, that's all I got. This is a little bit more interesting. Okay, a protein will fold into its three-dimensional structure. So if you haven't had any biology yet, if we're looking at proteins, they're a sequence of amino acids. So it's just a string of a whole bunch of individual atoms. Okay, carbons, nitrogens, and oxygens. That string is probably on the order of thousands of atoms. Right? But just like any normal string, if you take a string and cut a strand of it, right, does it just stay as a length? No. Depending on where you put it, it balls up, it folds up. Okay? Those folds with a standard piece of string are just kind of random. With amino acids or proteins, they aren't exactly random, and we'll see different patterns that come out of them. Those patterns are what we then reference when they come together to result in a folded protein. Okay? So we're talking about the intermolecular forces within your strand coming together to make the folded protein. Which sets us up with our question. Is the folded protein more or less energetically stable? Does the folded protein have higher or lower entropy? Again, at your tables. So what do we get? Where do you want to start? Do we want to look at the energy or the entropy? What's that? Entropy? Okay, cool. We're going to look at the entropy. What do you expect?
Lower.
Why should it get lower? It's not as free to move around. Okay, you're unfolded, that's a floppy chain. As soon as it's folded, it's not floppy anymore. It must obtain these individual helices shapes. You've changed its possible motion states. Okay, or you've decreased them. Okay, which means we should end up with a lower entropy. Now let's consider the actual energetically stableness of this. Okay? What's happening when we go from unfolded to folded? The entropy will change. The question is how.
Hydrogen bonds.
We're making hydrogen bonds. Okay? And the making of bonds is exothermic. That releases heat, which means if it's releasing heat, heat's over here, your folded state is more stable than where you started. Kinda, sorta? Okay. I jumped the gun a bit on Tuesday, so I won't do it here. We're looking at our protein folded and unfolded. Okay. We could look at an energy diagram. Your products are more stable than your reactants, so we're looking at that loss of energy. Okay. That's giving us our delta H. Okay. When we look at our entropy, okay, again, we've reduced the possible states, okay, of motion for it, which is going to suggest we're looking at a lower entropy as well. Kind of make sense? All right, now the fun question, back to it. Is this going to happen at high or low temperatures? Okay, I would argue we could even take a step a little bit further back from that and say, is it spontaneous or non-spontaneous? Right? So really all we're doing here is the exact same thing we did here. We're now picking just another example and now saying, where does it fall in this magical quadrant? This magic set of boxes we've now relied on for all of these questions. We're now relying on it for protein structure. Do you think this little box is important?
For sure.
Yeah. Where do you think this box should show up? Your cheat sheet. Is it already there yet? No? You should fix that. Okay? get that on your cheat sheet so you're now ready to function moving forwards. Okay? Oh, well, as I go through that. So negative, let's see, does the slide actually do it for me? It doesn't, does it do it? Doesn't do it for me. So negative delta H, negative delta S, sorry, all the way back. Where does that put us? Spontaneous at low temperatures. So as long as we're cool, we would expect As long as we're cool, we would expect the protein to go through and fold. What happens if we increase the temperatures?
Not spontaneous.
It should switch. It should no longer be spontaneous. It should be non-spontaneous. Okay? And if the folding process is non-spontaneous, what's happening with the unfolding process at high temperatures? It becomes spontaneous. So we could look at that forward reaction and the reverse. Okay? Do we have evidence of this already being a true thing that we've seen in our real world experience? Yeah? Did you have breakfast this morning? You should have breakfast. It's good for you. Okay? Gives you energy to make it through the day. What's a common breakfast food? Eggs. Right? And you could eat them raw, I guess, but most people don't do that. Instead, what do? We cook them. In the process of adding that heat, what happens to the egg material? It changes its state. It coagulates because what did we do? We just denatured all of those proteins. We just unfolded the protein structures within the egg, which then caused a phase change for us. And arguably makes it taste better. Might add some salt and other stuff too. But. Make sense? Okay. Increase. Which then takes us to this day, whatever that is. Alex is due this Sunday. I have no idea if the top date is ever right. I believe those office hours are correct. I do want to point out towards the retakes. Number one, did anybody try to do a retake yesterday between 2 and 4:30? Good. Because I wasn't in the lab room and I entirely forgot about it and I felt really bad after the fact. So you should be sending me emails to confirm where I'm going to be at. Okay. In theory, I try to notify you if I'm going to move around. One of those move arounds, this Friday, I'm not holding my standard office hours. Okay, so 2 to 3:45, I think is the standard office hours. I'm not there. I'm dealing with more interviews, just like last Friday. But I will be there from 10 to 12:30.
What are you doing interviews for?
Hiring new chemistry faculty. Yeah. We're supposed to have 6 faculty. Right now we have 5. Arguably we have 4 because Dr. Schneblin's out too. So we're a little overworked. So yeah, we're trying to deal with that.
Wait, do we have to do the retake quiz even if we can't do the retake?
If you can't do the retake because you scored too high, you can't do the retake. Sorry.
No, but it's because it's worth 1 point. I was just asking, so does that not matter?
What?
There's like a quiz in Canvas for it?
Yeah, it's like still worth 1 point.
Oh, yeah, you should still do that assignment. That's really just a tracking thing.
Cool.
So I believe if you look at that assignment in Canvas, you're supposed to do that before you take the retake.
Okay.
Right? That's supposed to be a reflection back on your overall process. Did we not talk about that? I built it afterwards, didn't I? I did talk about it? Okay. You may have just missed that. Okay? Reflect backwards on the process and let me know some stuff. It's not part of your grade. So if you actually look at the assignment, it should say do not include in grade calculation. At least it does for me. Okay? That's just a tracking to verify that you submitted that in. Does that make sense? And then you would send me an email, let me know, and you do the retake. We good? Okay. So we think of reactions typically going in one direction, from reactants to products. Right? Our big summary of the pieces that we've looked at so far, thermodynamics tells us whether that reaction will happen. Okay? This will happen is spontaneity. Okay? Is it spontaneous or not? That word is a charged, loaded word. Because when we think about combustion, particularly spontaneous combustion, what are we thinking about? I want to pretend I heard somebody say it. I think I heard explosions. Okay, we're seeing people spontaneously combust into a big fireball. Everybody in this room is spontaneously combusting. You are converting glucose into CO2 and water. That's part of your respiration process. That is happening naturally. Okay? How do we know when we stop living, what happens? We stop breathing, but we continue to produce CO2 and water as our bodies get decomposed by other organisms. Okay? That's a spontaneous process. Okay? We have to be careful to not bring in spontaneity as far as speed, because chemists don't refer to spontaneity with speed. Speed is now kinetics. That's an entirely different subject. That says nothing about whether the reaction will progress or not. Okay? It just says how fast it progresses. Kind of, sort of? Okay. When we looked at that protein, what we addressed is a new concept. Right? Because when we looked and evaluated that, and the organic chemist in me is cringing like crazy over these arrows. If you take organic chemistry, maybe you'll learn that. Okay? When we considered the protein unfolded to folded, it wasn't just it folds. The protein could also unfold. So we would now add this concept of these two arrows. We can get our reaction progressing forwards, or we could get it progressing, backwards. All reactions have this. Okay? The fun thing about all of this is that if we consider our reactants and our products on our energy diagram, this was our delta G, right? And if I go forwards, what's the sign on that delta G? Our delta G would be our products minus our reactants, and if our products are lower in energy than our reactants, it would be negative. Let's pick a number for it. Random number. We'll call it negative. Okay, you gave me an option. There we go, negative 30. What if I do the reverse? Now it's going to be positive because I'm going from my products up in energy. It's now positive. Do better. Do better than it's just positive. It's positive 30. The forward and reverse reactions have the same, I think the correct word is magnitude or absolute value of your number. The sign is the only thing that changes. That's it. Right? That's kind of a neat system. Right? If we consider the speed of the reaction, would we expect the speed of the reaction to be the same forward versus reverse? No, why not?
Activation energy is different.
When we talk about the speed of the reaction, our forward has an activation barrier between the reactant and the transition state. That's our activation area. That's what's controlling the speed. What's controlling the speed for the reverse? That's the activation barrier, which means the rate of those two reactions may not be equal. Could they be equal?
Yeah.
When?
When like the activation energy is the same for both sides.
If our activation energies end up becoming equal. Does that make sense? Okay. Which now sets us up for an activity. So for the sake of for the lecture recording, we're just, we'll walk through the directions anyway, so everybody can pay attention to it if you missed. We're going to model some reactions. So within your tables, okay, there are a couple of tables that are odd. You can divide up your partners however you want. Okay, we need a partner A and partner B. The front tables are the ones closest to me. So these two tables here, partner A starts with $100, partner B starts with 0. Okay. The middle tables, running right through here. Okay, partner A starts with 50. Partner B starts with 50. The back tables. Okay, partner A starts with 50. Partner B starts with 150. That's your starting point. What you're now going to do is go through and exchange money back and forth between partner A and partner B. Okay? The rule, partner A gives B 40% of what they have. Partner B gives A 30% of what they have. Okay? This is done at the same time, so A doesn't give 40% and then partner B calculates. Okay, does that make sense?
Say that again.
A doesn't give B 40% and then B now goes 30% of what they now have. They're both done at the same simultaneous thing. So as you go through, your number's going to go down and up, right? Per each of those systems. We want to go through and repeat this for 10 exchanges. Okay, this is going to involve a calculator. The math isn't horrible, okay, but it is going to involve a calculator and punching it in. Okay? I forgot to mention sig figs on Tuesday, and people were like trailing out like 10 digits of sig figs. Okay? If you just want to keep me 3 digits, I'm fine. 3 digits is all you need, okay, to run this cycle. Kind of make sense? We understand our rules?
Since you gave me 0, or since you have 0 at the beginning, you're going to give me 0.
This is roughly what it's going to look like. I already forgot which table this is. Partner A starts with 100. Partner B starts with 0. 40% of 100, okay, is $40. So partner A gives B $40. Partner B is going to give 30% of whatever they have. What did they have? 0. 30% of 0 is?
You broke.
0. You don't give anything to partner A in that first case. Does that make sense? All right. You would then move to a new system. Your numbers have changed. Go through, run the process again. Run the process again. Run the process again. Okay. I'm going to give you guys some time to go through and work through it. But eventually what we're going to ask for is what were the numbers from group 1, 2, 3 after 10 exchanges. Make sense? Okay, I'm going to pause the recording. Data that we can manipulate this. So for group 1, so our table's up front. What 2 numbers am I looking at?
42.8.
Is that A?
Yeah.
Okay. In theory, the table's up front got something ballpark 42, whoops, that's a whatever. 42.9-ish and 57.1. You guys just confirmed. Did you guys get similar numbers? Cool. Okay, so we are seeing it balance out. A potential theory is, oh, it's going to balance out at 50-50. Is it balancing out at 50-50? No. Okay. Middle tables.
It's the same thing. So for A, 42.8, and then for B, 57.1.
42.8 and 57.1.
0.1.
Okay, that's interesting. You guys started with different numbers, though. Are you sure you didn't screw it up?
Who knows?
You're positive. Okay, cool. In theory, did you guys get the same set? True. Interesting. Same set. So you start with different numbers, and yet at the end of these exchanges, you end at the exact same point? That's a little weird. Okay. How about the back rows? I know I had yours.
85.7 for A and 114.3.
Okay. Well, you guys got way different numbers. Do we notice anything interesting potentially come out of this?
That would pretty much just be double. They have more.
Group 3 started with twice the amount of money. If we look at the final ratio, it's twice the amount. It doubled out. So when we're running this, when we look at this forward and reverse reaction, A passing to B was our forward reaction. B passing to A was our reverse reaction. What did we note eventually happened? You ended up transferring back and forth the exact same amount of money, which means your total change stops changing. Right? You're still transferring money back and forth, so the process is still continuing. This is what's known as a dynamic equilibrium. Dynamic because it's still transferring. You're still moving money around, but it's an equilibrium because it's balanced. Okay? All reactions will trend to this balance, this equilibrium system. Again, given enough time. And I cut everybody off as far as time, just because we should advance a little bit. So what we're talking about is a dynamic equilibrium. Okay? Number one, our reactions will always go in both directions. Okay? And we achieve this equilibrium, this balance, when the rate of the forward and the rate of the backwards equal each other. What was the rate forward and the rate backwards in each case? That was how much money you were transferring. You had the exact same amount being transferred. You've reached that equilibrium. When we've achieved this equilibrium, the amounts of the reactants and products will remain constant. That statement gets a little bit dangerous and misleading because what we then start to assume is that it's static and it stops. It doesn't stop. The reaction still continues. It just continues in a way that doesn't change the overall output or our overall view on the system. Okay? A relatively simple, straightforward example we could look at, if I look at a container of liquid in it, and I put a straw, okay? The straw has how much liquid in it? Nothing. If I put that straw into the liquid, now what happens? The liquid starts to rise in the straw. Does it rise forever? No, it eventually reaches an equilibrium where it's at, technically it's not 100% even. If you go through and actually look at it, it's usually a little bit higher. Okay? It reaches a point where it stops changing. Does that mean water is not coming in and out? No, water is still constantly moving. Okay? I'm still getting water moving into the straw, and I'm getting water moving out of the straw. Okay? That's still happening, but the visual output that we look at the end looks static. Okay? We have to remember it is not static. Your reaction does not stop, it continues. What does this look like for a plot? Concentration versus time. Have we seen concentration versus time plots before? Yeah? When did we see those? When we looked at kinetics. Did they look like this plot? No? Yeah, they did actually. They looked like that part of the plot. Okay? Because that's where the rate was changing. That's what we cared about. Equilibrium now says, I don't care about how fast it's going initially. I just want to see when the rate becomes static or unchanging. What does it mean? What happens to my concentrations of all my species and all that fun jazz? Okay? So it's the same plot. We're just looking at a different part of it. Okay? And again, that part is heavily time dependent. We're looking at a time that is way beyond anything we've seen before. Okay? For it to level out. Okay? This is going to get derived later on, but I get so excited about this that I want to talk about it. Okay? Let's simplify our reaction here. A goes to B, B goes to A. What's the rate for our forward reaction? Assume this is a mechanistic step. What would the rate be for our forward reaction? Careful. Our rate for the forward reaction would be our rate constant times the concentration of A. If we've reached equilibrium, we know this is going to equal the rate for the reverse reaction. What's the rate for the reverse reaction equal? Don't tell me K times A. K times concentration of B. Is the red K the same as the blue K?
Yes.
No, one's red, one's blue. Okay? And for those people who are like, that was a jerk thing. It's technically a different K. It does mean a different thing. You're looking at a forward direction versus a reverse direction. Okay, so the color coding was just a secondary bonus. Okay, so we could add language if we don't have that color coding. The rate constant for our forward could be K sub F. F for forward. What's the blue one? We could go with backward. No one uses backwards. We use R for reverse. Okay, why is this special? Well, now what can I do? We get this fun equation. Why is this equation interesting? Well, I have a constant times a concentration, and I have a constant times a concentration. And what do mathematicians like to do? Group like terms. So I'm going to keep my k forward over here, and I'm going to bring my k reverse over. And we're like, well, why is that a big deal? It's not a huge deal, except I have a constant divided by a constant, also known as, it's only 1 if they're the same. Remember, they're not the same. So this constant divided by a constant is a constant. So I could simplify this down, and instead of calling that kf over kr, I could call it a new constant. Since it's a new constant, I can invent whatever the hell I feel like to represent this new constant. And what do we choose? You said it. K. Not to be mistaken for our rate constant k, because the rate constant k is lowercase, and this k is capital. And because k's handwritten are so clearly different when we look about capital and lowercase, somebody made a real stupid maneuver for picking this as our symbol. Okay? But that's our notation behind it. There is a little bit of kind of logic behind this, right? Okay? If I take a lowercase k divided by a lowercase k, I generate a new constant. That new constant is based off of k's. So why not make it a capital K versus lowercase k? Okay? So capital versus lowercase makes a lot of sense. K was a stupid choice. Try T. Lowercase t versus capital T. Those look different, except T is time. Dang, pick a different letter. Okay? But this is where this concept of the balance of our products and reactants comes into play. This is known as our equilibrium constant, okay, or our equilibrium ratio. It's the ratio of our products to our reactants. Okay? And it doesn't matter where we start, that ratio is constant. That's exactly what we just saw in the demonstration. Table A ended up with a ratio between those. I don't know, we didn't actually quantify what that number was. Okay? Groups B ended up with the exact same numbers. Why did they have the exact same numbers? They started with the exact same total. That's why they had the same numbers. But the ratio becomes the critical part. Because what happens when we increased the total to begin with? Our numbers are changing, but what happened to the ratio? Stayed the same. Okay? This is our concept of equilibrium. So no matter where we start, okay, given enough time, all reactions will achieve this balance, this equilibrium, where we're exchanging back and forth the exact same amount of reactants for products and products for reactants. This is what's known as the equilibrium constant. Sometimes you could clarify that capital K by adding an EQ after it. There's no EQ for our rate constants. So adding the EQ can help. Right? But you'll also sometimes see it as KC. What does KC stand for? Another word that begins with C. Concentration. Okay? Because when we're looking at that equilibrium, it's the product's concentration related to our reactant concentration. Okay? And that would be reported in units of molarity. Would we report units of molarity for gases? Probably not. We could, but we'd probably use something else for gases. What would we use for gases? How do you measure gases? Pressure, which means we could also look at a K, P, if we're looking at the pressure relationship. Okay? There's also a Ka and a Kb that you'll study later this semester. Okay? All of those are now special cases of when we're looking at an equilibrium constant. Right? It's typically written out in terms of concentration, and if we were going to go through and write an expression for it, our K is going to be our concentration of our products divided by the concentration of our reactants. What did we do with the 2 when we looked at rate laws? Good answer. We didn't do anything with it. We didn't know what to do with it. We had to know some more information with what to do with it. When we move into equilibrium, guess what? We use it. That's now going to be my exponent. Is that exponent an order? Nope, it's not an order. Don't start using it as an order. Okay? But that exponent needs to get factored in. Okay? I am aware of where we're at as far as time. I wanted to get a little bit further, but it is what it is. Okay? Where we're going to start on Monday is writing the equilibrium constant expression for each of these following reactions. Okay? Remember, what do the brackets mean? Concentration. K equals concentration. What is concentration? Molarity, which is moles per a given volume of your solution or the container. Consider that when writing out these equilibrium expressions.